Hi everybody, this is going to be the next tectonic geomorphology lecture. This is mountain building and climate tectonics relationships. So we're going to look first at how mountains are built, not in any great detail though, and because I want to focus more on the influence of climate on tectonics and vice versa. So first, this is a digital elevation model of the topography of the planet, and we sometimes refer to this as hypsometry, which is just looking at the distribution of elevations across the landscape. And so if we look at the entire planet, we see that Earth has kind of two dominant elevations. The first is about 4 kilometers below sea level, and that's the blue that you see. So the blue on this image is not representing water, it's actually topography. So the darker colors are deeper, and the lighter colors up into these kind of red colors would be the higher elevations. So we have a lot of elevations that are about 4 kilometers below sea level, which the oceans are more or less filling in. And then we have a lot of elevations between 0 and about half a kilometer above sea level. And so that's what you see as the continents. So these two elevations are more or less representing the two different types of crust on the planet. So the oceanic crust, which hopefully you remember from intro geology, is thinner, more dense, and it sits lower on the mantle. So that's why you have this 4 kilometers below sea level. And then the continental crust is thicker and more buoyant, and so it sits above. And you notice that some of it is higher than others, where you have these mountain ranges. So how do we maintain those mountain ranges? How are those large mountain ranges held up? So there's two different types of what we call isostasy, and isostasy is the balance of gravitational forces versus buoyancy that determines how high something sort of floats. So we can think about isostasy as an iceberg floating on the ocean, or in this case, crust, sort of sitting on top of a denser mantle beneath. So there's two types of ways that high elevation can be maintained. The first is called area isostasy, and this is where high elevations are compensated by crustal roots. So what this means is that anywhere you see, high elevations, you assume that down below this area you have a deeper section of continental crust, which is shown as dark. The white would be mantle rocks, and so that is mainly peridotite, very dense, kind of olivine-rich rock. So it's not fluid, of course, it's actually solid rock, but it's denser. And so then the continents more or less float on top. So this is the first way that you can maintain high mountains, is that you have some sort of compensating low density material below those mountains that are helping to keep them high. The second type is what we call Pratt isostasy. And so this is due to not differences in thickness, but lateral variations or differences in density. So in this case, the mountains, the high areas, are less dense. And this might be to different rock type, or it could be due to a difference in temperature. So this is the model here, and we're seeing that, for example, this yellow block is sitting higher than the orange block, but there is no crustal root down here. They're all sort of have the same depth. And so the difference here would be that this is just less dense. The yellow is less dense, and the orange is more dense. So where would we see this on the planet? Well, a good example is at mid-ocean ridges, where you are creating new crust, and as it moves away from the mid-ocean ridge, it gradually cools. And so that difference in temperature, that cooling, causes it to sort of sit lower and lower. So if we go back to this map, and I know it might be a little bit too small to see, but these mid-ocean ridges are high. You have the kind of a little mountain range in the middle of the Atlantic. And then as you move away, it gets deeper and deeper, lower and lower. So one of the primary reasons for that is that the crust cools as it moves away from its formation spot at the mid-ocean ridges, and therefore it sinks a little bit lower. And so that would be related to this Pratt isostasy. Third, the crust actually has some rigidity to it. So that means that it can hold a little bit of a load. It's not just perfectly fluid like the ocean or something, right? So it can hold a little bit of weight on it. And so we see that in some cases, mountains are held up by just the rock strength of the crust. And this generally has to happen on a very wide spatial scale. So the example that they're showing here is actually the big island of Hawaii, where you have this kind of big volcano. The big island is the largest volcano on the planet from the top to the bottom, if we consider the bottom down the bottom of the ocean. And the crust beneath it, there is no root down there. There's no compensating root, but the crust is actually sort of flexed a little bit and holding it. And you can actually see this bulge when they look at topography of the ocean floor on either side. Okay, so we've got isostasy, two types. We've got this rigidity of the crust as well. So how do we build these mountains? Well, of course, we can first look at where they occur, and the tectonic boundaries aren't mapped on this digital elevation model, but you're probably familiar with them already. But we have a kind of the boundary between the Pacific plate and North American plate, something like this. You have another subduction zone here between the South American plate and the Nazca plate, which is down into here. But if we look at these mountain ranges, so again, the Himalayas, boundary between the Indian Australian plate, which is outlined something like that. Most of these mountain ranges are forming at plate boundaries, right? Due to shortening and uplift. So how do that crust actually get raised? So the only way that you can get crust to rise up, where you can create mountains, is if you somehow thicken the crust somehow. So you have to stack it, because remember, if you just squeeze something together, if it doesn't thicken, it won't sit higher. It'll just stay, right? The elevation is a function of its buoyancy. So you have to increase buoyancy, and you do that by thickening that low density continental crust. So a couple of ways that this can happen is either by thrust faults. So this is, literally you've got a whole series of thrust faults that are sort of stacking the crust on top of each other, such that you're sort of creating these mountain chains. You're doubling the thickness of the crust. Folding, squeezing and folding of the crust and of the especially the upper crust, where you have typically sedimentary strata that can easily be folded. Ductile thickening. So oftentimes in the upper part of the crust, you have thrust faults and folds that are sort of enabling the crust to be thickened. But then down below, when you're getting into the ductile range of the lower crust, things aren't behaving brittly anymore. They are just ductily thickening, right? Just like you're taking a piece of clay or something and smashing it together. It may not break along faults, it's just going to grow thicker in the opposite direction. And then the fourth way that you can increase the thickness of the crust is by adding material to it. So in this case, we would be maybe adding plutons of magmatic rock. Say we have a big subduction zone going down here, and you are actually adding plutons to this overriding plate, and therefore it gets thicker and you start to form mountains. Now, erosion, of course, is constantly trying to tear down any positive topography. And there's an interesting feedback mechanism where the higher your topography gets, the more intense erosion is. And so erosion becomes more intense at high elevations. And this is typically the result of glaciers. So at a certain elevation, you're going to start to form permanent ice, and then you're going to form glaciers, and these glaciers are extremely erosive. They can erode at a much faster rate than rivers or just dry erosion. So there's a certain point, and this depends, of course, on latitude and the regional weather patterns, right? So at lower latitudes near the equator, glaciers are going to form at a much higher elevation because it's warmer than if you look at mountains up in the Arctic regions. It's already cold, and glaciers can form basically at sea level up in Alaska, right? But you would never have glaciers at sea level in, in India or the Himalayas. So it depends on latitude, it depends on regional weather patterns, but at some point there's going to be an elevation where ice forms and then this starts to tear it down. And the reason that this is a feedback mechanism is, as I'm going to show in the next slide or two here, is that as you start to tear down the mountains, or you start to remove material, usually that's not uniform across the whole area, right? The glaciers are just eroding valleys. So you get narrower and narrower valleys as you erode. And what that does is the isostatic compensation causes the whole mountain range to lift. And so your peaks actually get higher even as your average elevation decreases. So there's this initial tectonic influence, but then isostasy starts to play a role, and that can also contribute to further growth of the mountains. Okay, so why is there a mosquito up here? That was my example of a feedback mechanism. You get a mosquito bite, you scratch it, it just seems to itch even more. So isostatic uplift is the vertical movement of material due to removal of the deeper removal of material in the valleys. So if you erode mass off the top of mountains, the area will lift up to maintain isostatic equilibrium. So as a good analogy, of course, is an iceberg. Imagine you have a sea level here, and we've got a big block of ice floating, right? And there's going to be more of it down below sea level than above because it's less dense. And so you're standing here, and you want to, live on this iceberg, and you want to be closer to sea level. So if you start digging out, right, and you start to dig down and build yourself a little valley or something so that you can come down here and be closer to sea level, what's going to happen is you're removing mass here. So this whole thing essentially becomes a little bit lighter, and the whole thing will move up. So when you've removed mass, then what happens is the whole thing moves up, and I'll try to draw like a dotted line. This will be your new, elevation of your iceberg. So your peak, the top, has actually gotten higher even as your valley that you're digging has gotten lower. So what happens with isostatic uplift is the peaks actually get higher as you dig these valleys deeper. If you were to completely plane this whole thing off, right, then the whole thing comes up, and you'd have very little net change. You would actually decrease your average elevation, but if you're eroding in specific spots, your maximum elevations actually increase. So this concept means that we define two different types of uplift. And the term uplift refers to just vertical movement of material, of the crust. So first is what we call surface uplift. And this surface uplift means that your average elevation is rising, your mean elevation is rising. So if this is your mountain range or your iceberg at time 1, at time 2, the whole thing has moved up, and so your average elevation is increased. How can you do this? Well, this picture actually isn't correct. You can't just suddenly move this up unless the density was to get lighter. But usually what happens is you thicken the crust, right? And you've made it thicker down here, and so the whole thing rises. Rock uplift is referring to like a piece of rock. So if I were to imagine just one little piece of rock here, there it is at time 1, and there it is at time 2. So the elevation of that little piece of rock has changed. But the mean elevation, the average elevation across the entire mountain range, doesn't necessarily need to change. In fact, usually in this scenario, it would actually decrease. So rock uplift just refers to a piece of rock is rising relative to sea level. And surface uplift means the average elevation of the entire area is rising relative to sea level. So the only way that you can do surface uplift, I can't draw, but I'm trying to write out the word tectonics. That looks absolutely horrible, but you need tectonics, you need crustal thickening to get surface uplift. You cannot do it just from isostasy, but rock uplift could be solely due to isostasy, but there's also rock uplift occurring here. So there's a little rock there, and it goes to here. So in this case, the bottom case, you have rock uplift, but no surface uplift. In the tectonics case, you have rock uplift and surface uplift. Okay. So with that kind of background, now it's interesting to look at how climate has changed throughout late Cenozoic time and how that seems to correlate with the growth of large mountain ranges that we now see on the planet. So in late Cenozoic times, geologists have noticed that many mountain belts around the world have undergone an increased amount of uplift. And what's the cause of that? Could this, it was the original hypothesis is that tectonic rates sped up or something changed with the tectonic system, and all of a sudden we are creating these large mountain ranges. But people also notice that at the same time, the global climate has sort of, on average, has cooled down over late Cenozoic time. And by late Cenozoic time, I'm talking, generally about 10 million years or less, okay? So we're not talking about just the last ice age, we're talking about the end of Cenozoic time. So Pleistocene, Holocene, even into Pliocene. So what has been discovered is that there's these feedback mechanisms that are probably at play here. And first, if you cool the Earth, we seem to get a corresponding increase in uplift and erosion. Okay, so, and why is that? When you start to cool the Earth, you start to form more glaciers, and you actually increase erosion in these mountain ranges. And that increased erosion deepens the valleys, and the isostasy effect causes then uplift of the peaks. So you get an increase in rock uplift, but the average elevation of these things did not really uplift. The average elevation of these mountain ranges actually went down because you were removing material from that mountain range. But isostasy caused the peaks to get higher. So some people have hypothesized that the uplift of all these mountain ranges on the planet is actually due to climatic changes. So the climate impacted the topography. Or the opposite could be true. We know that if you get increased uplift of mountain ranges due to tectonics, what happens is that then causes more erosion and weathering processes. So the weathering of rock and turning, say, feldspars into clay, this actually consumes carbon dioxide. So the more weathering, the faster that things are weathering, rocks are weathering on the planet, the more you consume carbon dioxide out of the atmosphere, and that results in a cooler climate. Okay, so both of these things could be, exactly what the initial cause is may not be understood, but this is sort of a feedback mechanism. As you start to build mountains, you cool the climate. The cooler climate causes more glacial activity, higher erosion rates. That leads to more isostatic uplift, and it's just like keeps going around and around. Okay, so let's look at two examples here from the Sierras and then also the the Andes in Chile. Um, so if we look at the Sierra Nevada and we see here Yosemite Valley, um, people have pointed out that you have these huge glacial valleys, especially in the higher parts of the Sierras, and people have suggested that much of the uplift of the Sierra Nevada might be due to glacial erosion. So, the mountains that are there now may have originally been lower, maybe just half as high or even less, but cooling climate in the Cenozoic, these multiple ice ages that we experienced, caused increased erosion of these valleys, and that caused the peaks to rise. Okay? So there's still a big question. This hasn't entirely been figured out, as far as I can tell. There's still papers coming out in the literature that are arguing one way or another. But exactly when did the Sierra Nevada mountains rise and why is not totally understood. So here's a digital elevation model of California and parts of western Nevada. So these are the Sierra Nevada mountains. We've talked about them a little bit before. The highest elevations tend to be in kind of the southern two-thirds, southern half of the mountains. And we also see that there's a very big difference in the slope of the mountains on either side. So they're rather gently sloped towards the west, and on the east side you have a very steep slope. So remember in the last lecture we were talking about asymmetric mountain ranges. The Sierra Nevada are a perfect example. They cross-section view, they almost look like a kind of lopsided triangle like this. So one hypothesis about the growth of these mountain ranges is that they happened around 3 to 5 million years due to tectonic processes. So normal faulting in the basin and range at the end of the Miocene affected the eastern part of the Sierras, and you have big normal faults here, and the Sierras are in the the footwall block of that big normal fault and lifted up the mountains. Okay. The second hypothesis is that the mountains were actually high for a very long time, maybe for tens of millions of years, and a smaller amount of uplift occurred just between 3 and 5 million years ago due to cooling of the climate. So when I say the mountains were high for a very long time, they were not as high as they are now, but that there was a big sort of plateau out here possibly. That might have been a few thousand feet lower, but then as these glaciers formed, removed material, isostatic rebound caused the mountains to come back up. So these things have been, two different explanations proposed for the development of this modern Sierra Nevadas. And remember that if it's surface uplift, which implies that your average elevation is increasing, the crust must be thickening in order to do that, then it has to be a tectonic cause. If there's no surface uplift and it's just rock uplift, then this is probably isostasy. So we think that we should be able to figure this out then, right? All we need to do is see if the average elevation of the Sierras today is less or equal or greater than the average elevation of the Sierras 5 million years ago, right? We can easily measure the average elevation of the Sierras today. The big problem is, how do we measure average elevation from 5 million years ago? That it's not a very simple thing to do. So one way that people have tried it, and there's been different methods, was using hydrogen isotopes to look at kind of infer paleo elevations of different spots within the Sierras. People have tried to look at fossil plants, look at kind of biologic zones throughout the mountain ranges to see if we can, identify that where, for example, where there's big pine trees growing now and where you hit the tree line, if that used to be lower than it is today. All right. So I just put this in as just one quick example of a recent publication where they're trying to figure this out, but it actually turns out that this is a very complicated problem, trying to understand or measure what the paleo average elevation was of an area. Really, the only A good way you can do this, I think I talked about it 2 lectures ago, is if you have sedimentary deposits that were going across an area of some sort, and then that whole area has been lifted up, then you have this remnant marker. But that doesn't, we don't have that in the Sierras. A second example is from the Andes in South America. Same argument, is the uplift of the Andes due to climate or tectonics? So some people, an example, this paper from 2003, has proposed that increased uplift of the Andes Mountains in the Cenozoic was due to climate cooling and the climate becoming more arid. And they said this also would have resulted in less sediment being delivered to the subduction trench that is just offshore of the western edge of South America. So this would be a climatic cause, whereas other studies have said that the uplift is probably due to a change in the rate of convergence between the Nazca Plate being subducted underneath the South American plate. So again, same type of problem. We know for a fact that changes in climate affect topography and affect the growth of mountain ranges, but figuring out whether tectonics or climate is responsible for each individual mountain range is not easy to do. So I'm going to finish off this lecture with another example. This is from the island of Taiwan, and this is kind of a really cool study that was done years ago that shows the interaction between erosion and tectonics. So Taiwan is a mountain belt that's about 4 kilometers high at its highest point. It's relatively young, geologically young. It just developed over the last 5 million years. And it has pretty high precipitation rates, about 2.5 meters per year, right? So a meter is 3 feet. So we're looking at something like, almost 8 feet of precipitation per year. And most of this is occurring during, these low tropical storms that come through called typhoons. So you have pretty intense erosion rates, but at the same time, you also have active uplift and earthquakes going on. So this is a measure of erosion rates, with the red being higher erosion rates. So this fully red is 30 millimeters per year of erosion, and the blue being areas of lesser erosion rates. Okay. So one very interesting thing is that people have noticed that when you have earthquakes, you oftentimes strip the hillsides of soil and the shallow part of the rock that's exposed, as well as the vegetation. So earthquakes can sort of increase erosion rates. And then that, of course, could then lead to isostatic uplift if you are removing more material. But at the same time, and so here's an example, erosion rates increased in the area of the Chi-Chi earthquake. This was in 1990, I believe, and it affected a major fault that's drawn in black right here on the northwest side of the island. And so, you have a little bit of uplift from these earthquakes because it's a big reverse fault that's lifting the central mountains of Taiwan in each earthquake. But at the same time, you've got increased erosion, which can contribute to uplift. Okay, so that's not too surprising. We've kind of known for a while that earthquakes can cause uplift of mountains. That's basically how they grow. But what is interesting is that people are starting to note that the inverse also sometimes happens. So the increased erosion that occurs from typhoons coming through seems to have a correlation with earthquake activity. So what they're doing in this figure is they're mapping 2 recent typhoons that came through and the increased erosion that occurred along the tracks of these typhoons. And then they can compare the location of that increased erosion, and they find that they get increased seismic activity in that area, probably because the removal of material due to erosion is lightening the hanging wall, the fault. So it sort of unclamps the fault a little bit and allows it to move. So this study is suggesting that, you know, not only does climate affect tectonics or the elevation of mountain ranges on a short-term scale, on a long-term scale, but possibly even on a short-term scale in a matter of years. Individual storms actually leading to, you know, earthquakes shortly after and uplift. So this is kind of a newer idea that's come out, but it's pretty interesting that explores the interaction between tectonics and mountain building. So that's it for this lecture, and I'll see you guys in class.